Hello everyone, my name is Aidar, and in this video, exercise 9, we will run and visualize climate projections. First of all, you need to open RSMinerve with your calibrated model and make sure it's working. Validate start. Yes, it is working. Next, we need to make sure that you have the right database that has the future simulation bias corrected data for the time period 2012-2099. If you don't have that, you can choose the group where you want to import this data, then click on the import, choose the folder where you have this data and choose the CSV file extension. Then here you need to import all the future simulation data with the BCSD code into the RSMinerve. Make sure that you add the bias corrected with the code BCSD bias corrected data, because if you add the future simulation without this BCSD code, then it means they are not bias corrected, and you should choose the bias corrected ones with the BSCD. If you don't have these CSV files, you can go back to the climate processing chapter in the R code and run the future simulation preparation, processing, and bias correction scripts, and the script will generate the bias corrected CSV files. After you add future simulation bias corrected forcing data to the database, you need to add the glacier runoff projection for different scenarios, and after that we good to go. Next, you need to adjust the data sources for the station, where we need to change the historic observation rescale to one of the future simulation forcing data. For example, let's choose the future simulation GFDL SSP scenario 126, and the glacier runoff series identifier should be changed from historic observation to the SSP 126. After that, we can validate and start the model, but here we have warnings that there are no data, so I forgot to change the solver time period from historic one to the future simulation. So we have the date till the 2010, so that means that the dates after 2010 will be future simulation. That's why 2012 is considered in this case future simulation. Now we can validate, and we have no warnings right now regarding that, and we can restart. But we have the error value was either too large or too small for int32. This problem on my computer is solved easily by changing the recording time step from 1 once to 1 day, then validate, start, and it will compute. You can click on the comparator or the junction to see the results of your model. And here you do not need to pay attention to the objective function indicators, because objective function is the comparison of the model to the observed values. And since we don't have observed values in the future, we don't need to pay attention to that. And it's good idea to check the data, for example, in selection and plots, where we can select by checking the box what to visualize and then press plot. For example, right now I selected the snow water equivalent for all 10 elevation bands, and I see that I have right now a problem with the initial values of snow water equivalent in the elevation band 10. And in order to save the results of the climate projection, you can just go to the junction, press on the value, and copy the whole table. But it's very stupid way to export it, so let's go to the selection plots and choose some new model selection. For example, I already created this queue down. For example, like this, you create a new selection and call it, for example, result. And here you choose the junction and choose the junk down and press the plot. And here are your results. And you need to press the export results to and choose the folder. For example, we can create a new folder calling it results. So let's give this file a proper name. So it was the discharge data. Let's put Q. Then it was the future simulation with the bias corrected files, and it was the GFTL SM4 GCM model, and it was the SSP scenario 126. It was the river basin Zerafshan for the time period 2012-2099. Save as type CSV and press it save. Now we can check the directory where we saved it, and here our results in the CSV format. It will have the long format for your data. Now you should do that to every model in RSMinerve, just clicking here, choosing the next model, IPCL for the same SSP. Now press validate, start, and for next model I don't need to change the glacier runoff because it has the same scenario. Now we go to the selection and plots, choose the result and export it again. Choose the similar name but with a different model name, IPCL CM6A. Save it. Be careful and don't make stupid mistakes, and repeat this process for all the future simulation model. Don't forget to change to the SSP 245 when you use the 245. Validate, start, and don't forget to solve such problems like this before exporting your model. After you export all climate projections for each DCM model and for each SSP scenario, we can proceed to the next part, to the R code, where you don't need to change much. First part is the library, where you don't need to make any changes. Second part is data and parameters, where you only need to adapt the directory to the monthly data, decadal data, and GIS data similar to the previous codes. It's important to adapt this directory where you will save figures that are generated by the script. Then you can run the second chapter, the analysis of discharge data. And in this chapter, we work only with the historical observed discharge data. Here we can see the seasonal diagnostics for monthly data, for decadal data, and change of monthly discharge. Inclined red line signifies the change within the months. Next, we do the validation of calibration. And here is important step where we specify directory to our results files, climate impact results. Here we can run it and save the graph in the directory that you specified here. Then we plot the monthly discharge values here, similar graph that you could see in the RSMinerve. Then the analysis of climate impacts, where we visualize the climate impact results. And first is the development of discharge. Here we have a time series plot of climate model ensemble with a daily discharge. And now we plot the model specific results in individual plots and put everything together with a patchwork. Here, section for GFDL model, IPCL, MRI, and UCASM models. Next, the annual discharge. After that, we do the 5-year mean discharge. Next, interannual discharge variability for each period. Period 0, period 1, period 2, period 3. If you don't know what are these periods, then you can have a closer look to the script. And in the part 4.2, we have definition for each period. Any date prior 2012 is period 0, any date after 2040 is a period 2, and any date in between is period 1. And finally, any date after 2070 is period 3. Then we can proceed with a tabular form where we have coefficient of variation, interannual range, interquartile range, and standard deviation for each period. Then we compute another table with the scenario coefficients for each scenario for each period. Then we have percentage of years above a threshold. Here we have a percentage of years, and the threshold is computed here. Threshold equals quantile 35th uh, percentile of discharge values. Next, percentage of years below a threshold, similar thing, but below. Next, we have mean per period discharge values. After that, we have changes in discharge seasonality in form of hydrograph. Here it is, we have it for IPCL model, but if you want to visualize for a different model, we can adapt it here, just comment and uncomment what you need. For example, the UCASM1 model. If you want, you can adapt the name of the file which will be saved in your directory. Next, we compute index changes in the distribution of seasonal water supply. First is warm versus cold season. This graph shows how much discharge ratio we have in the warm season against the cold season. If you are interested in the formula, how it's calculated, you can always check the code here. For example, we have it here, the warm season divided by cold season. Next, we do similar graph, but this time it's for actual total seasonal values, not just for the mean seasonal discharge values. Here it is. Next, we compute index changes in the distribution of seasonal water supply semester 1 versus semester 2. Next, we compute the ratio between the quarter 3 divided by other quarters. After that, we do the development of flow characteristics, where we calculate and visualize the flow exceedance curve for different periods. And that's all for this script. This code is not strict rule on how to visualize this data and how to do that. You can adapt it to your own needs and you can make changes in your code to make it better for your case. If you want, you can make changes here. For example, you want to compute a different threshold, different ratio, not with the quarter quarter 3 divided by sum of the 4 quarters, but you want to do it with the sum of 2 quarters. Then you can easily adapt it by changing the name here and the formula here, changing the quarters and other values if you need it. That's all. That was exercise 9, climate projections. Thank you for watching this video. Thank you for watching this whole series. This tutorial series is created by Hydrosolutions and is supported by the Swiss Agency for Development and Cooperation as part of the SAPPHIRE Central Asia project and CROMO-ADAPT project. Tutorial videos were created by me, Aidar Zhumabaev, and my colleague Adrian Kreiner. If you have any questions, feel free to write us via email or down in the comments. Goodbye.